Okay, let's get started. We're a couple minutes early, but that's okay because there's a couple of logistical things I want to go over before I get into the content. The first logistical item I want to go over is I've gotten a few questions about lab groups, and I realized I didn't clarify this last time, so let me clarify now that all of your laboratory assignments and your final project are group projects. And I strongly advise groups of 3. Groups of 2 are okay. Groups of 1, you're going to die. It's too much work. Groups greater than 3, work distribution becomes challenging. So I strongly advise groups of 3. If you go to the course site, which I have up somewhere, there's a link here, Lab Partner Preferences, under Meta Information and Due Dates. If you click that, it'll take you to a Google form where you can specify the folks with whom you would like to work in this class, or alternatively, you can request to be assigned to a group, and I'm happy to assign you to a group if you would like. The only constraints on lab group partners is I ask that all members of a lab group be members of the same lab section, simplifies things, and I ask that all members of a lab group be enrolled in the same class. This is a co-listed class, 4760 and 5730. So I ask for everyone in the lab group to either be in 4760 or everyone to be in 5730. Okay. The other logistical thing I wanted to mention is each lab group will be given a little kit that contains Raspberry Pi Pico and a bunch of accessories that you'll need for programming this thing. The idea being that you can take this kit home and work on it on your own time. For the whole semester, you'll be allowed to take that kit out of the lab. For this week only, I'm going to ask for folks to please leave it in the lab. And it's only because in the first 2 weeks of class, there's a lot of add drop going on as folks finalize their schedules. So we'll just keep the hardware in the lab for the first week or 2, and then you're welcome to take it with you. One final logistical thing is I had a few folks enroll in another course that I teach, which is ECE 4920. It's a technical writing class. I just want to clarify that this course is a prerequisite to that class. And you might actually be interested to know if you're enrolled in this course, because maybe you want to enroll next semester. In that class, what we do is take your final project from this class and rewrite your web page as a magazine article and submit it for publication in a technical magazine. And last semester, we got 14 or 15 articles published in Circuit Seller and in Servo Magazine. One of which, by the way, let me just show you. One of which got on the cover of Servo, Matt and Louis' article, which is kind of cool, right? So if you're enrolled in that this semester and you're enrolled in this class this semester, I'm sorry, but please unenroll from 4920, but please re-enroll next semester once you finish your final project. Okay. Any questions from anyone before I get started on content? Okay, so what I want to do today is to provide, last semester I did a really quick overview of the hardware peripherals that are available in the RP2040. I want to do a slightly more detailed tour of the internals of the RP2040 this lecture. And then I also want to introduce the software infrastructure that's in place for configuring and controlling that hardware. And I'm going to talk about this first, sort of conceptually. I'll show you some diagrams and pictures from the data sheet, and then we'll look at some code. This kind of stuff, the best way to really get an understanding from it, or of it rather, is to look at demo code. So we'll spend some time in class looking at the demo code. In particular, this week in lab, what you'll be asked to do is download the course demo code, build it, and load one of those demo programs onto the RP2040. I want to demo that whole process here so that you see it, and if you have any questions about that process, you have the opportunity to ask those questions. In this class, for every laboratory assignment, you'll be given a demonstration project from which to start, a starting point. For Lab 1 only, there is a repository on the course demo code Git repo. If we take a look at this, called Lab 1 Incremental. The demo code from which you'll actually start Lab 1 is audio beep synthesis. It seemed a little cruel to me to just dump this on you because this is also new. So the notion of this repository is it culminates with the demos that you'll use for your week 2 and week 3 checkouts, but builds up to them incrementally. So over the course of the next week or 2 in class, what I'm basically going to do is use this repository as the source of demonstrations to talk through, so that by the time we get to like Wednesday of next week, we will have incrementally built up to this demo from which you'll start. And each of those demos, I'll just point out, is documented. So you can read along with me, and please do. Okay. Okay, so all that being said, what I want to talk about today, as I said, overview of the internal hardware available on the RP2040, the software hardware levels of abstraction, an introduction to the C software development kit, the SDK. This is a software library provided by the Raspberry Pi company for configuring and controlling the RP2040, and then I'll show you an example in code. And before I get into all those details, I want to make a slightly philosophical point, which is I'm often asked, what is this class about? And I'm supposed to describe it in like a sentence or two. The way that I describe what this class is that it's a class about hardware, software, co-design. So it's a class where you're asked to build projects that involve hardware and that involve software, and where you get the two to work together in a such that they complement one another, such that the hardware is doing stuff that hardware is good at, software is configuring and controlling that hardware, and doing stuff that software is good at. And I want to just make the point that may be obvious to some of you that when I say hardware, what might come to mind automatically is stuff like sensors, motors, actuators of all sorts of varieties that you would plug into the GPIO ports of a microcontroller. And what I'm talking about includes that stuff, but is not limited to that stuff. As I suggested last time, the RP2040 and essentially every other microcontroller comes with a whole library of internal hardware peripherals that you can configure and control and use in your projects. So hardware, software, co-design certainly includes the stuff that you'll breadboard on, a separate whiteboard and interface with the microcontroller. It also includes utilization of these hardware peripherals that I'm going to talk through in a little bit more detail today. Okay, and this is a diagram that I hallucinated this morning that tries to illustrate the levels of abstraction between the hardware and the software for this particular microcontroller. And what I'm trying to point out here is that you can think your model for the microcontroller and the relationship between the hardware and the software in here, you can think of hierarchically, I think is appropriate. Where at the bottom of this hierarchy, you have all of the peripherals that are available in the RP2040. You have things like dedicated SPI hardware, doing SPI communications. You have pulse width modulation, peripheral, timers, a bunch of DMA channels, PIO, etc. This is the stuff that's in there. Fundamentally, at the lowest level, the way that all of this hardware is configured and controlled in the RP2040 and in basically every other microcontroller is by manipulating the values of registers. And as many of you are aware, what a register is simply a place in memory where the system looks at the data at that place in memory and interprets it as configuration or control information for this hardware stuff. We're going to look at the data sheet and look at some of these registers. What we'll see is that there are thousands of them, right? Thousands and thousands of these registers. And the behavior of some of them is coupled with others of them, right? So if you make a certain register configuration over here, that has consequences for stuff over here in this other register. So in principle, you could write programs for the RP2040 that configures and controls this stuff by directly touching these registers. But nobody does, because it's so cumbersome. And the Raspberry Pi company and other companies that make microcontrollers recognize this. And so what they do often is they'll put together SDKs, software development kits, that abstract these low-level register manipulations into function calls. So suppose we wanted to configure the SPI channel for a certain clock phase and polarity and a certain data writ. We could certainly go into the data sheet, find the SPI control register, set the appropriate bits, and that would work, right? What the SDK does is abstracts that to some function called something like SPI init or something. We'll take a look at exactly what it's called. That takes a series of arguments, and those arguments would set things like clock phase, clock polarity, data rate, all of the parameters for opening an SPI channel, right? So it makes working with the device much easier. And then you will be working at this level of abstraction mostly. Maybe occasionally you'll come down here and touch a register because you want to do something bizarre or specific. But mostly you'll be working at the SDK level of abstraction. And then next week, what I'm going to introduce is a top level of abstraction, which is a proto-threads, which is not a Raspberry Pi thing. It's a lightweight threading library written by Adam Dunkels, modified by Bruce for the RP2040. This allows for us to set up our programs as concurrent threaded programs, which is convenient. So we can organize our code into threads using proto-threads. Each of those threads will contain a bunch of C function calls, C SDK function calls that are doing lower level register configurations to set up and control the hardware, okay? And we're going to revisit this a few times, but I want to present all this first, and then what I'm going to do today and over the course of the next maybe couple of lectures is talk through each of these levels of abstraction. And I'll caveat this by saying when I'm talking about this level of abstraction, you're not going to be working there that much, right? But in a class like this, where a class like this is a balance between what we expose and what is hidden, right? And this SDK kind of hides these low-level register manipulations, but it's very important for you to know what's hidden, because when your code doesn't work, which it won't, you know how to debug it, right? You can say, okay, what's this C SDK function actually doing? You go look at its implementation, figure out what registers it's touching, go and look at the data sheet and say, okay, what's it actually doing here? And what you may find is that behind the scenes, some SDK function that you're using is using a hardware resource that it might not be obvious that that resource is being used, that's causing some sort of contention with another thing. I'll show you an example of this, but for example, if I recall, I believe there's a high-level C SDK function called sleep, which just does what you expect for it to do. It's a blocking sleep for a specified number of microseconds. Under the hood, that's using these hardware spin locks, which I'll talk about, but it's a no-kidding hardware resource that you can run out of, right? So you could get yourself into a position where there's this obscure bug, you're not sure why the code isn't working. By understanding that this is just manipulating these, you can debug in an informed way. I'll demo all of this. Okay, so let me start by talking about the lowest level of abstraction, which is this internal hardware. And I'm going to do that by showing you a picture from the data sheet, which you should please all start perusing. I chose the RP2040 for this class for a lot of reasons. One of the major reasons that I chose the RP2040 is the documentation is fabulous. For a lot of folks in this class, among other things that this class introduces you to, reading technical documentation is one of the skills I hope you leave this class with. If you've never done that before, if you've never really dived deep into a microcontroller data sheet, this is a great one to start with, right? So it's part of the reason that I chose this for this course, is the documentation is just so readable. There's even jokes in there. If you read really carefully, it's almost like little rewards from Raspberry Pi that says, I can't believe you're reading this carefully. Here's a little joke. But in any case, what this is showing you is sort of a schematic view of the stuff that's inside the RP2040. And I'll start up here by just indicating that there are two processors. I talked about this last time. Each of these are ARM Cortex M0s. They share 26 interrupts. And the other thing that each of these processors is connected to is this block labeled SIO. SIO stands for single cycle IO. And I'm just going to expand what's in here for a moment. This contains, inside of it, this SIO, single cycle IO block, contains a bunch of peripherals that each of the CPUs needs low latency access to. No delays. So all the stuff in here, each of those CPUs can talk to in one cycle, as opposed to trying to speak to something through the bus, which requires, I think, 2 cycles to set up and load the bus transaction. Plus, if there's a lot of bus traffic going on, there might be a little bit of extra delay for communication through the bus. Communication from the CPUs to anything on the SIO occurs in one cycle. So what sort of stuff might that include? Well, there's a register in the SIO called CPU ID, which contains the ID of the CPU. If core 0 reads the CPU ID register, it returns 0. If core 1 reads the CPU ID register, it returns 1. So this provides a mechanism for your code to learn which processor it's running on. which is convenient. Yeah.
Does this have SIMD at all or no?
SIMD? I don't know what you mean. What is that?
Single instruction, multiple data. Vectorization?
No. Not to my knowledge, at least. I'll double check. I could be wrong about that. Bruce, do you have a comment?
It is a fully symmetric multiprocessor. There's no SIMD, there's no coordination between the processors at all.
Other stuff that's in here. A FIFO going this way and a FIFO going this way. So there's a 32-bit wide, 8-sample deep FIFO that you can use to push and pop information from one core to the other core. A good way to synchronize these things too, incidentally. 32 hardware spin locks. What these are is, say you have some application where each of the cores is trying to access a shared resource. Maybe there's some global variable that they're both accessing and manipulating. You certainly don't want CPU 0 to access that shared resource while CPU 1 is working with it. These spin locks provide a mechanism by which one of the CPUs can lock out the other CPU. There's 32 of these, sort of. This is a good example of why it's good to read the data sheet, because you could shoot your foot right off with this. Bang. There's 32 of these. However, if you read the C SDK guide, the section for hardware_sync, the hardware interface library for the synchronization resources on here, what you'll discover is that spin locks 0 to, I think, 25 have, they're used up by something or another. For example, the C SDK itself uses a subset of these spin locks. So you can use spin locks, I think it's 25 to 32. It will let you say that you want to use spin lock 5, for instance. I don't believe it will throw an error. I'll check that, but I don't think it will. But man, that's going to create some really subtle bugs, right? So read the data sheets. And then each has access to a few other things. Those integer dividers that I talked about last time, the interpolators I talked about last time, each has a pair of those. And each has direct access to the GPIO ports. So that's the SIO. And if we keep looking at the other stuff that's included here, 12 DMA channels. I talked about those a little bit last time. Each of those can do a single 32-bit transaction per CPU cycle. You open the box up, turn on the RP2040, it's going to be running at 125 megahertz. So you do the math, that is a lot of bandwidth. It's a lot of data that you can move around. And I've overclocked these to 250 megahertz, and they don't really even break a sweat. I haven't experimented with much higher than that, but I have read that you can get up to like 300, 350, and things remain relatively okay. You void your warranty above a certain rate, but that's okay. This is a void your warranty kind of class. I read an article yesterday that one, I think he was an intern at Raspberry Pi, managed to run one of these things at 1 gigahertz. He had like some special cooling setup and overvolted it, and it ended up destroying itself, but it did indeed run for 1 gigahertz for a little bit. The USB connection, SRAM organized in 6 blocks. There's on-chip ROM. This contains like the bootloader and such, stuff that you won't really be manipulating. The onboard cache that communicates out through the QSPI interface to the external flash memory that's holding your program code. These PIO ports, which again, we'll talk about in some depth, but these allow you can write assembly code for each of these PIO ports to directly manipulate the GPIOs. And then you can have the DMA channels communicate between the PIO coprocessors and, say, processor 0 or processor 1 to do high bandwidth communication from the processors to the GPIO ports. These can control all the GPIOs. So you could write programs that are toggling the GPIOs, according to some specific sequence, all 30 at a time, if you care to, which actually fascinatingly makes this a reasonable replacement in some applications for FPGAs. We can talk about that a little bit, but pretty fascinating. And then a whole bunch of internal peripherals, a couple of SPI channels. The green coloration here is indicating that you can form a connection between these to the GPIO ports. So you can map SPI channels to the GPIO ports, which makes sense because we have to hook it up to something external. PWM, pulse width modulation, hardware peripheral, some UARTs, internal timers and internal real-time clock, internal I2C channels, analog to digital converter and temperature sensor. We'll spend some time next week talking quite a lot about this ADC. The ADC clock runs at 48 megahertz. A single ADC sample always takes 96 of those, which means this is a 2 microsecond per sample ADC. Reset control, power on state machine, etc. And the GPIO ports. Okay, and a couple PLLs here, which you will actually probably want to play with. In lab 2 in particular, when you're trying to get as many of those voids as you can, overclock the CPU and you suddenly have more cycles to spend for your animation, right? So you're probably going to want to do that. And then as I was suggesting, you can map a subset of these peripherals to the GPIO ports to have them talk to the outside world. And this is an image from the Raspberry Pi Pico datasheet, which is showing you which of those internal hardware peripherals can be mapped to which GPIO ports. So for instance, GPIO port 0 here could be configured to be the RX pin for SPI channel 0, the data pin for I2C channel 0, or the TX pin for UART 0. Or to give another example, GPIO 26 could be configured to be the ADC MUX 0 input, or the data channel for I2C channel 1. So you can see that it's not arbitrary. You can't map an internal signal to any GPIO port, but you can see which GPIOs can be mapped to which peripherals here.
Pico does not have onboard debugger. What device are we going to use? I'm
sorry?
Pico does not have onboard debugger, so what device are we going to use?
So the question was, the Pico does not have an onboard debugger. What debugger are we going to use? You can, if you want, use a Pico to debug another Pico. You do so using these pins down here. You can set that up. You can alternatively work with these things without a debugger, which is a little trickier. However, it sure makes programming it easy because you just program it right through the USB port. So it's up to you. You can figure out what workflow works for you. Questions about this stuff? Okay. So then, all of this internal hardware, as I suggested previously in this image, this internal hardware is configured and controlled by registers. Maybe it's worthwhile. Let me just give you a quick example. So if we do RP2040 data sheet, let's just show where this kind of information lives here in the data sheet. Let's take a look, for instance, at the SPI list of registers. So you can see these are all the registers that configure and control and provide information about the SPI channel. Let's take a look, for instance, at this one, which is the control register for SPI channel 0. And you could go in here and say, okay, it's a 32-bit register. The top 16 bits are reserved. And then this is telling you what each remaining bit in that register is doing. So you could configure your SPI channel 0 by manipulating this. And that would be perfectly reasonable, if a little tricky to get exactly right. Alternatively, we can use the C SDK, which I'm going to talk about next. And before I do, I want to talk about the general arrangement of the SDK, the software development kit, which is also arranged hierarchically. And at the bottom of the SDK hierarchy, there's a series of libraries in a folder. When you look at the RP2040, the whole library, it's arranged in folders. There will be one there called hardware_regs or reg library or something like this. In any case, if you look at an example, if you look at a file in this directory, and we'll do this later, what you'll find is a whole huge list of pound defines, which gives a name for each register. So it associates a readable name for a register to its place in memory as specified by the datasheet, right? So it turns that just a whole list of memory locations into something that it associates that location with a name that is somewhat readable and that maps to the datasheet. So we can look at that name and say, okay, I know what I'm touching here. I know what I'm working with. The next level of abstraction up is the hardware structs, which organizes all of these registers into C structs. And it organizes them in such a way that they represent the memory mapped layout of the RP2040. So for instance, there's going to be a struct which with some name called something like SPI hardware, SPI_HW. And if you look at all the fields of that struct, what you'll find is that it contains all of the named registers for the SPI channel, right? So that then if we want to go manipulate the control registers for an SPI channel, we can do so by manipulating the fields of this struct. The advantage of which is that it's a little more readable, right? It organizes things nicely for us. The next level of abstraction up, you'll be doing most of your work at this level of abstraction, are the hardware support libraries or the hardware interface libraries. These provide an API for interacting with each piece of physical hardware. So it's at this level of abstraction that those C functions that I was talking about that abstract the low-level register manipulations into function calls, those are in the hardware support libraries. So that function with some name like SPI init that takes a bunch of arguments that configure and control the SPI channel, that will live in the hardware interface library or the hardware support library for the SPI channel. Again, we'll look at this in code, but I just want you to have some sort of an internal model for how this is organized. And then there is indeed a higher level of abstraction where there are some libraries. The folks that put this together recognize that a lot of developers might want some capability that would require a couple of different pieces of hardware. So there are these higher level libraries that will include a handful of these slightly lower level hardware interface libraries to give you some higher level capabilities, things like sleep, right? Which might require a timer, it requires some mechanism for blocking, so it uses one of these hardware spin locks. But you can imagine that a capability like that might require a couple of those internal pieces of hardware, so it includes those automatically and gives you a higher level API for those sorts of things. Okay, so that was a lot really quickly. What I want to do next is look at a very simple example to start to illustrate how all this hooks together in code. This is an example. All this content, it can really only be presented all together, right? Because it only sort of makes sense when you see how it fits together. But it's a lot to see for the first time. So what we're going to do is look at it here, look at some code, come back and revisit this, look at more code examples. You'll practice it in the lab, and this is all going to start to make sense. But for now, what I want you to have is some internal model that involves hierarchies, where the RP2040 itself has real hardware. We configure and control that hardware by manipulating register values. The C SDK, which is provided by the Raspberry Pi company, abstracts those low-level register manipulations to function calls. And then this we're going to talk about next week, but this just makes writing our code convenient. Okay, it allows us to set up threaded environments. And this C SDK is itself arranged hierarchically. At the bottom of that hierarchy, oops, wrong one. At the bottom of that hierarchy is all the registers associating names with each of their memory addresses. Then all those registers get arranged into structs, just for our convenience. And then the hardware interface libraries or the hardware support libraries are a bunch of C functions that go through and manipulate the fields of these structs. In doing so, configuring and controlling the hardware peripherals, right? And then the higher level libraries give you some higher level capabilities that might require a few of these support libraries. Sound okay? All right, so then the next thing I want to look at is the simplest possible example to illustrate how this works. Let's go here. So when you're learning a new programming language, what's the first piece of code that you write? Hello World. Anybody know where that came from? Piece of trivia. Who created Hello World?
Some guy at MIT. That's my guess.
Kernighan. Anybody read Kernighan and Ritchie? The guys that made C? Okay, it's like the classic C programming book. In any case, Kernighan created the Hello World example, which we now all use. In any case, when you're learning a new programming language, you do Hello World. When you're learning a new microcontroller, what's the first program you write? Blink and LED. So yeah, so let's look at one of those. And then as I said, we're going to layer complexity up on this rather quickly to build up to the demo code that you'll use for the next checkout. So what I want to do is, let's go to the course website. Another just brief thing is, I know it costs a few extra minutes for me to go access this stuff in real time. I want you to see where I'm getting the stuff that I'm talking about so that when you go to sit down in lab and you go, I know Hunter talked about something and I don't know where that lived, you see where I'm getting this stuff. So it costs a few extra minutes here, but I think it's worth it. In any case, this is the course website. If we go down to the links underneath daily use links, you'll see that the first link there is the course demo code. This is a Git repository that I put together to help you in this class. It's arranged by lab. So lab 1 contains demo code for lab 1, lab 2 for lab 2, lab 3 for lab 3. This lab 1 incremental, as I already mentioned, incrementally builds up to the lab 1 demo code. And then there's some other stuff here that you might be interested in for final projects or just for interest. There's some things here that drive stepper motors, VGA graphics demos, that kind of thing. Let's look first at the lab 1 incremental repository, particularly at Blinky. When we go in here, we're going to find 2 files. We're going to talk about each of them. There's a source file and the cmakelist.txt. I'll talk about this in a moment. The SDK uses cmake to configure and control the compilation process. It takes a little bit of getting used to, but actually I think once you're used to it, it's incredibly convenient actually that they do this. In any case, I want to look first at the Blinky code, which is quite short. Before I do this, actually, as we talk about this, the other thing that I want to demonstrate is what you're going to be asked to do in lab this week, which is download that demo code repository, download the SDK, and build it. There's a write-up on the course website about how to do this. I know that it's useful to see this stuff in real time sometimes, so let me just do that quickly. What you're going to do, this is, I have a remote desktop connection to one of the lab PCs. So when you log into the lab PC with your NetID and password, that's what this is. You'll go to the Start menu, go down to Visual Studio Code 2019, and select the debugger developer PowerShell for Visual Studio Code 2019. Not the Windows PowerShell. This won't work if you just use the Windows PowerShell. It has to be from that Visual Studio option. Navigate to your documents folder. Okay, make a new directory. I'm going to call it Pico. You can call it whatever you want. Go into Pico. And then we want to clone 2 repositories. The first thing that we want is that C SDK, which comes from Raspberry Pi. So we can do git clone -b master github.com/raspberry pi/pico sdk.git. You don't have to write that down. It's provided on the website, but it's useful to see these things. And then we actually have to update that module. So we'll go in there and do git submodule update init. This takes just a second to run. The next thing I'm going to do is clone in the example repository that we were just looking at in GitHub. I'm going to do git clone -b master github.com/vha3. That's me, Hunter Adams, RP2040 demos.git. Okay. The first time that you log on to one of these lab PCs, I'm doing this live because in part I expect there might be some errors associated with this step. The first time you do this, you have to set a couple of path variables. So in particular, we're going to set the Pico SDK path to the folder called Pico SDK, which will be 2 directories rather up from where the project code lives. I'll show you this in a second. And the other one that we have to set is Pico toolchain path, which lives at program files x86 GNU ARM embedded, this folder. Okay. The reason that I'm demoing this live is for this next step, because we set these two path variables, the next thing that you have to do is close this and reopen it. And I know that people will forget this, and we need to close and reopen in order for those path configurations to be in place. But in any case, so then we can go back to our directory here. You'll see that we now have the repository of demos. We now have the SDK. We'll go into the demos directory. Make a directory in there called build. Go into the build directory. And we're going to call a CMake function that prepares that build directory for building. And that's a little bit obscure, but it's CMake directory and make files. This is preparing us to build. Okay, and then we have a couple of options. What I'm going to do is call just nmake. That builds every project in the directory, which the first time that you do it takes a couple of minutes. We could alternatively, as I'll show you a little bit, tell it to build just one project in that directory, which takes less time. It only takes a considerable amount of time the first time you do it. Every subsequent time, it doesn't take nearly as long. I'll mention too that the third directory that the third repository that you may be interested in including here is one called Pico-examples, which is a whole repository of examples for the Raspberry Pi Pico that the Raspberry Pi company has put together. Really useful to also have, right? So you might consider getting that as well. In any case, we can now run nmake. And as I said, this will take a few minutes, so as this is building, we'll look at the code in the browser, but this is now building all the projects. So let's go back and look at the Blinky demo, blinky.c. There's not that much going on here, but that's the point. The first thing that we do is include a library called pico/standardlib, stdlib.h. This is one of those higher level API libraries, okay? So we include a library that we're going to use. We pound define LED_pin to 25. This is because if we look at that pinout diagram, we'll notice that the LED is attached to GPIO 25. Right, so it's just for readability. Now instead of placing 25 everywhere, we can just use LED pin. And then we drop into main, which, as everyone in this room knows, main is special, right? There's one main per program, and your code starts executing at the top of main. Was there a question?
You think you could just zoom in a little bit?
Yes, absolutely. Better? Okay. And the first thing that happens in main is we call a function called GPIO_init. This is an example of one of those C SDK functions that is abstracting lower level register manipulations into something that's readable. So presumably this is doing something like initializing a GPIO pin, GPIO pin 25. Suppose you were going through some demo code and you encountered a function like this and you weren't sure what it did. How would you investigate it? Okay, well, what you would do is you go to the RP2040 C SDK guide, and we'd scroll down here and look for the section on GPIO. And then within here, there's some information. Incidentally, this is kind of an interesting table. This is listing every GPIO port, and it's telling you all the signals that could be mapped to that GPIO port. It's kind of a nice resource, actually, to know that that lives there. And we'd scroll down, and we'd find a whole list of functions. Among them should be one called GPIO_init. If the world makes sense, it'll be here. Yeah. And OK, so now this is telling us what that function is doing. What we can see is that it initializes a GPIO port. So it enables I/O on that port and sets the function of that port to GPIO SIO. That SIO that I was talking about previously, the thing that both processors can communicate to with low latency. Remember that that had a connection to the GPIO ports. So this is mapping that particular GPIO port to the SIO to say the processors are going to drive it. It's not going to be driven by any other hardware peripheral. We could change that mapping. but when you call GPIO init, it's attaching it to the SIO. It clears the output enable, sets the pin to an input, that is to say. Why would it automatically configure a GPIO as an input? Any thoughts? Is an input high impedance or low impedance?
Low.
High. It sets it as an input, which is high impedance, which protects it, right? So it says, I know you want to use this as a GPIO. I'm going to automatically make it an input. If you want to use it as an output, you better have the circuit set up properly to not blow this thing, right? So it's protecting you from yourself. And then as an argument, all that it takes is the GPIO number. Okay. So that's the process. You know, if you're going through the demo code, you encounter some SDK function that you want to figure out what it's doing, open up the SDK guide and you'll find it in there, and it'll explain what's going on. And I'll show you in just a little bit how to go even deeper than that if you want to. Is that still building? Yeah, almost done. So we initialize a GPIO, which, as we just learned, that sets it to an input and maps it to the SIO. The next thing that we do is change some of those default configurations. In particular, we set its direction to an output. We don't want it to be an input because we want to drive an LED, right? So the two arguments for this C function call, we could go look it up in the SDK. I don't think that's necessary. The GPIO pin that we want to configure, and in or out, input or output. So now we're setting it as an output. And then we drop into the while loop that loops forever and calls a few more of these SDK functions. In particular, calls GPIO put. We're going to set that output, that GPIO pin that is configured as an output, to either high or low. We're going to say, this GPIO pin, set it high, wait 250 milliseconds. Same GPIO pin, set it low, wait 250 milliseconds, and so on and so on and so on. Okay? Let's see if that code finished. There's one more thing I want to show you here today. Yes, it did. So now everything's built. And what I want to show you is, if we open up our documents folder, we'll find that Pico directory that we created from the command line. We open up that Pico directory. We'll find the SDK that we cloned in and the example project that we cloned in. If we go into that demos directory, we'll see all the code, right? This is exactly the same as you would look at in the browser. It's just exactly the same code. And that build directory that we created. Really conveniently, when you compile code for the RP2040, all the stuff that the compiler generates, all the machine code, gets consolidated into that build folder. It's kind of nice. It doesn't end up spread out, and it doesn't make everything else messy. It all goes into one folder. So if we look in that build folder, what we'll find is a bunch of stuff that the compiler made. And in particular, we'll find a whole bunch of folders here with names that are identical to the folders in the upper directory that we were just looking at, right? This contains the compiled executables for each of the projects in each of these folders. So we were looking at Blinky, which lives in the lab1 incremental directory. So we can go in there. We'll find Blinky. And in here, we'll find a whole bunch of compiled code. And the one that's going to be particularly useful for you is the one with the extension .uf2. This .uf2 extension. The mechanism then by which you'll actually program your Pico is you'll hold down that little boot select button on the Pico and plug it into the PC. It will appear to the PC like an external memory device, a flash drive, and you'll drag and drop this onto what the computer thinks is a flash drive, and it programs the device. By the way, it's annoying to unplug and replug and unplug and replug. So alternatively, you can put a button, an external button between a pin labeled run on the Pico and ground. And if you add one line to the CMake file, which I'll show you in just a moment, it allows for you to, instead of unplugging and replugging, you can just double click the button. I really recommend you do that. It makes it a lot nicer. So in any case, that's where the compiled code lives. And if we cared to, we could go into any of these other folders and find the compiled code for, say, Lab 3, a PWM demo. You could drag this on, right? So that's where that all goes. The next thing that I just want to highlight is, let's open up this code in Visual Studio. I was talking, I belabored the point quite a bit that each of these SDK functions is under the hood just doing register manipulations. And I want to kind of illustrate the construction of this SDK with an example. So for instance, let's investigate this GPIO put function. So we can go to definition. Let's look particularly at this one. So when you go and see what GPIO put is actually doing, what we discover is, in this case, it's actually calling another SDK function called GPIO set mask or clear mask, depending if we're setting it to 1 or 0. Let's look at set mask and see what that's doing. So we're going into the SDK here. So we should be crawling down those levels of abstraction, right, towards the registers. So let's go here, go to definition. Aha, so set mask, you can see, is touching a field of a struct called SIO hardware. A field named GPIO set. Let's go look at that struct. Okay. GPIO set is set to this register named called SIO GPIO out set offset. So now, incidentally, where are we in this SDK? We're in the hardware structs level of abstraction, right? This is where all the registers are being organized into structs. But we could go even deeper. Let's go check this out. And what we'll find now is we're in that hardware registers library of the SDK that I was talking about that includes just all the registers, and it associates readable names with their memory locations. So in particular, this one that we were looking at is at an offset of hex 14 from the base address of the SIO peripheral. So if you really wanted to investigate this, the next thing that you could then do is go to the data sheet. Go to the data sheet. We'll go to the SIO section, and let's see SIO. Let's get a little bit more information about that particular register. Okay, I said offset of hex 14, GPIO out set. And what we can see is that at the lowest level of abstraction, that GPIO put C SDK function is going down and touching this register, which what you can see this is doing, it's a 30-bit register that is performing an atomic bit set on GPIO out, setting one of the GPIOs. Now, incidentally, there was a branch point in that GPIO put where one function was called if we were setting it to 1, the other one was setting it to 0. We could crawl down these levels of abstraction again, and what we would find, I haven't done this, but I'm almost certain, is that the other option is touching this register, which is an atomic clear of a GPIO. So I'm trying to show you how you can investigate code that might be unfamiliar to you for this particular system. So you're going through the demo code. You're cruising through, say, you're cruising through this demo code. You encounter some function that's unfamiliar. First place you can go is the C SDK guide, right? And you see what they have to say about that particular function. You want to investigate it even deeper. Why would you want to investigate it deeper? Maybe you're trying to figure out some subtle bug, and you suspect that maybe deep down there, you're touching some piece of hardware that some other SDK function is also touching, and you want to see if that's the case. In order to do that, in Visual Studio Code, you can travel down the levels of abstraction to figure out, okay, which registers am I actually touching? Then you can go to the data sheet and investigate those registers, and also read that chapter of the data sheet about the hardware peripheral that you're actually touching, right? So this is kind of the workflow for this particular device. How much time do we have? Okay, 2 minutes. So let me then just introduce the other file that's in this example directory, which is the cmakelist file. This is essentially, all that this does is tell the compiler what to do. It sets some configurations for the compiler. So for instance, it gives the executable a name. We're calling it Blinky. You could call it something else. The only constraint here is that in your repository of projects, you can't give two projects the same name, same executable name. This is nice because when I called nmake and said to make every project in that demo folder, I could have alternatively said nmake Blinky, and it would have just made Blinky. We list out all of the source files to include in this project. First argument is the executable to attach it to. In this case, there's only one source file, blinky.c. If we had some library, for instance, a header and source file that gives you a bunch of VGA primitives, like you'll use in Lab 2, we might have a few extra .c's listed here. We link to the SDK libraries that we're going to be including. In the C file, we included pico/standardlib. So pico_standardlib is represented here. What we'll see next time is when we include more libraries, we have to list those libraries here. The Pico add extra outputs. You need this if you want to generate one of those UF2 files. Okay, so you'll have this at the bottom of every CMake. Next time, we'll look at another example, right? And we'll reinforce this example. Cool. I will see the Wednesday folks soon.